Alright, this is my second attempt to record lesson 8-1, error approximation. There's a bunch of people here. Ani, Rahul, oh god, now it's recorded. Rakesh, Connell, and Emerson. So, we'll see how many times it takes to record that with, Connell and Rakesh in the room. Here we go. So, for a convergent alternating series, when we're approximating the sum of the series by only using the first n terms, the error will be less than or equal to the absolute value of the n plus first term. This is the next term, or the first unused term. That paragraph is the only thing you really have to understand, but it's incredibly confusing at first read. So let's go through it slowly. So we're talking about a convergent alternating series. We're going to approximate the sum by only using the first n terms. So I'm going to say, hey, I know what the value of this series will be. Let's just use the first n terms, and we'll see how that goes. The error in that approximation will be less than or equal to the absolute value of the n plus first term. Absolute value, n plus first term, or the absolute value of the first unused term. So let's talk about what an approximation is. Let's talk about what an error is, and let's talk about what a remainder is. If I have a building, and I say the building's about 1,000 feet tall, that's an approximation. I would like to know how far off that approximation is. I would like to know the error of that approximation. In this case, the error is how much remains to be added to the height of the building. So if I found out the building's actual value was 1,002 feet, if the actual value was 1,002 feet, and my approximation was 1,000 feet, then I'm talking about an error of 2 feet. That's approx. The error in my initial measurement was only 2 feet. Does that make sense? So, we're first going to try to approximate the sum. This series has some value. Maybe it's 0.1 to the millionth. I don't really know. Maybe it's 1, maybe it's 5, maybe it's pi squared over 6. It's some value. But the idea is its value from n equals 1 to infinity is approximately, look at that, see how squiggly equal, you have to write it. It's only ever equal for using infinitely many terms or ... So the first term would be clear, we're starting at 1, negative 1 squared times 1 over 1 factorial. Now if you're feeling good, you can do this in your head, but I know a lot of people still struggle with this idea. 1 over 2 factorial, negative 1/4 times 1 over 3 factorial. So that's 3 terms, but I want to use 6 terms. Negative 1 to the 5th, 1 over 4 factorial, negative 1 to the 6th, 1 over 5 factorial, one more term, plus negative 1 to the 7th, 1 over 7 factorial. Oh my gosh, not 1 over 7 factorial, 1 over 6 factorial. So it's not always going to get to 6. It could have gotten to 5 if we started at 0, okay? Now again, I would want you guys to be trying to simplify this as you do it, so you don't have to waste time rewriting. But this is how I'm getting what I'm writing right now. I don't know how Word opened up. That's pretty dumb. Sorry. Okay. 1 minus 1/2. You should have your factorials memorized up to 5. If you know 5 factorial, 6 factorial is easy too. Now, in case everyone's freaking out, like, oh my gosh, I have to memorize that too. I hate this BC test. It just makes you quicker. Whenever I say this stuff, I mean, you'll just get more points if you have it memorized. You always want more points. And if you don't want to have it memorized, you can always just do the recursive thing. Times 2, times 3, times 4, times 5, times 6. Okay? Now, you can punch that all in the calculator. In general, watching these videos, I can't show you the calculator. That's what I found out this morning. This thing does not work without being plugged into the main projector. It's really annoying. But if you punch that all in, I would say that equals 2.63194. I'm using equals here because these 6 together do equal that. These 6 together are approximately that. So this value is an approximation of that value. Remember, when it converges, this is some number. Let's say it's pi over 6. Let's say it's pi over 6. Sure. Then that's approximately pi over 6. That's what I'm saying. So when I'm asking about the error here in our approximation, I'm asking how far is this number off from the actual value, which we'll say is pi over 6 again. To answer that question, and this was the most confusing thing, I think, for my BC kids, the people in the actual classes here, the error is the remainder. That's the surprising thing. The error in this approximation is exactly how much was left to add over here. And that's relatively surprising. So, if we just pay attention to the words, if we just focus on the words here, the error is the approximation, the error is the remainder, and we're talking about actual minus approximate is less than or equal to the value we're about to get. So, next, find the upper bound for the remainder. I'm going to say the remainder, which again, if you look at the homework, there's lots of different words for this. That's what makes the homework card. The remainder, which we're saying is the error, is less than or equal to the absolute value of the next term. What was the next term I would have added in here? Well, n would have been 7. So this absolute value is not really necessary. The idea would be that this value is about 0.000198. So what's surprising here is that that's how accurate we got by only using 6 terms. By only adding 6 things together, I know that this decimal place was accurate, this decimal place was accurate, this decimal place was accurate in the approximation. Why do I know those were accurate? Because these are all zeros. So the next thing you add is not affecting it at that level. It's just not. So how far off was this approximation? It was about this far off. So what I'm saying is find the upper and lower bounds. So since actual, I think these are the equations that would help people, minus approximate was going to be less than or equal to the absolute value of the error, or the remainder. So the absolute value of this was less than that. To find a upper bound for the actual sum, I could solve for actual here. And I'll do this again with real numbers in case that's helping you. So I know actual minus approximate was less than or equal to the absolute value of the error and greater than or equal to minus absolute value of the error. Solving absolute value equations like this and inequalities is very, very important for calculus. Very, very important in BC at least. So make sure you understand. I got rid of the absolute value bars by having a plus and a minus. That's what we were talking about for differential equations too. Now, if you're thinking, oh, but that's minus an absolute value, it's just going to be positive. No, this minus is outside. All right, so to solve for actual, I'm going to add approximate to all three sides. Three sides, yes. Three sides. So I would have the approximate value minus the error is less than or equal to the actual value, which is less than or equal to the approximate value plus the absolute value of the error. And again, everywhere I say error could be remainder. Everywhere I say error, you could replace with the word remainder. That's what's surprising with series. The error is what remained to add. Like in the building example, if I stopped measuring the height of the building at the 17th floor out of 20, the error in that approximation would be exactly the height of the last 3 floors, right? Whatever remained to add. So that's how the math looks conceptually. Here I go. So the actual value is bounded above by the approximation plus the error, and bounded below by the approximation minus the error. So, here we go. The actual value of my series would be bounded above by the approximate value plus that error right up there, and it would be bounded below by the approximate value minus that error up there. Okay? Now, this is not some formula you have to memorize. You should know this from science. I know many of you don't. It's okay. How far are we off? We take the approximate, we add the error. That's the maximum the value could be. That's how big the sum could be. So, putting it all together, I would say the maximum value, the upper bound, would be 0.6321429. And the lower bound, or at least a lower bound, would be 0.631742. Okay? So that's giving me the full range of values here that my sum could have obtained. There's no way that the actual value... Oh, I should have relabeled it maybe over here. So we would call that the upper bound. And similarly, that would be the lower bound. And they're bounds because there's no way this value could be bigger than that, and there's no way this value could be less than that. So we've trapped it up until that decimal, up until the thousandths place. And if you think of 1/1000th of an inch, that's very, very fine accuracy. That's the kind of engineering applications this has. Now, this lower bound is actually kind of weak. Why do I know it's weak? Because I know this value would have been positive. I know the next value was going to make it bigger. So actually I can use just the approximate value, but that's a little advanced. I talked about that in BC, and I think that was more confusing than it needed to be. So, approximate minus error, approximate plus error. That's all we're talking about. Right. So now I want to approximate this, it's a different series, with an error of less than 0.001. So error less than 0.001. So this is an alternating series, and if I want the error for an alternating series to be less than 0.001, what's the error for an alternating series? I want the absolute value of the first unused term to be less than 0.001. That's what I'm talking about. I just want that, the first term I don't use, to be less than 0.001. So the algorithm, the way we get this, is actually pretty simple. There's a simple way to keep track of the error. It's just the first term I'm not using. You might have to watch this part of the video more than once if my BC class is any indication. A lot of people didn't like this thing. That should all be red, right, based on the convention I was using. So here I'm saying, okay, so what's the first term? N equals 0. What's 0 factorial? It's 1. Negative 1 to the 1, negative 1 to the 0 is 1. Okay, so I have to at least use one term. What would be the first unused term here? If I stopped here, if I said this, if I said this was approximately 1, which you all know is a silly estimate, you all should know, the next value would be negative 1 squared, negative 1 to the 1, that's why it's negative, 2 times 1 factorial, 1/2. So, here's the key idea. If I wanted to approximate with 1, my first unused term would be 1/2. Is 1/2 less than 0.001? You need to be able to know this. Here, if I stopped here, the error would have been 0.5. So, this would be right if you were allowed to be wrong by 0.5, which you'll never be asked to do that. That's a huge error. That means the value of this series would be bounded between 0.5 and 1.5. There's too many values between there. That's way too not specific. 1.5 miles versus half of a mile, right? Running that extra mile would make a lot of a difference. You want to know how much of that mile you have to run. So we keep going. The error there was too big. So I would use this term. If I use this term, the error of the next side is 1 over 4 factorial. So this is a very calculator active section. 1 over 4 factorial, 1 divided by 24. If you computed these two terms, if this was your approximation, the error here would be 0.041666, okay? Yeah, I said it. So, you have that would be the error if you stopped at the first two. Now, I wish I could cover it up. Actually, I can with like a box. Here, I'll just draw a box. Waiting. Trying to draw. Boom. Great. Boxes don't cover up that? Yep, great. That's so stupid. Oh, math. I know what I can do. I can erase it. So if we said all I wanted to do was use those two terms, the error would have been 0.046. Is that less than 0.001? No. So I have to continue. I'd have to use this, or else it would be the first unused term. And if it was the first unused term, that would be the error. So, n equals 0, 1, 2, n equals 3. Minus, because I can at least do negative 1 to the third in my head, 1 over 6 factorial. So just to be clear, that was the value for 4. So now, if I wanted to use these three, this would be the first unused term, 1 over 6 factorial. Let's see what the error would be. What would his error be? 6 factorial is 720. The error would be 0.001. Oh, 3. Okay. 9. Less than. Is that less than that? No. So if I stopped for the first three terms, that would be the value of the first unused term. The first unused term would be 0.001. That's not good enough. So I need to include that also because it would not be small enough. So stop worrying about it. 4, negative 1 to the fourth would be positive 1. 2 times 4, 8. 8 factorial. That's some humongous number. One divided by 8 factorial is 0.00024. So that's the first term where if it were used as the error, then the error would be less than that, 0.001, because this is 0.001. This would be the error as long as I didn't use it. So if I chop that term off, that would be the error, and that would be the approximation. So I'm saying I want to use the first 4 terms and not this term. I want this term to be my error because that would be small enough. One more time. I wrote down the terms. 1, 1/2, 1/24, 1/720th, 1 over 8 factorial. I checked each term each time. Is it small enough? If it was the first unused term, would it be correct? Would it be less than 0.001? Yes? Good. It was only yes at this point. So, that's the whole idea here. That's why I'm going to use these 4 terms and not that term. You can also do this quite simply because you should be able to know that 0.001 is 1/1000th. 1 over 720 is bigger than that. 1 over 8 factorial is less than that. Okay? So that's how you would do it by hand. That would be your approximation. So again, they ask you to approximate. The approximation is everything that's not that. If that was the first unused term, then we didn't use it in our approximation. So the approximation, I don't know, you can try out, make sure you're using your calculator right. 0.540228. And we know that's accurate up to the 1000th place. This decimal cannot change. Okay. Use an elementary series to find the actual value of this. I'm pretty sure the BC test is Tuesday. I'm recording this on a Friday. I'm pretty sure this is a question that everyone's going to struggle with. BC kids, if you're watching it, good on you. It's very smart. because asking you how to find this value is going to be very, very hard if you haven't studied for it. I did it at lunch today, for instance. Trevor, Nathan, Rahul, no idea how to do this. Use an elementary series to find this value. That cues you in. There's 4 elementary series. There's e, there's sine, there's log, and there's cosine. Only one of those has 2n factorial in it. So I'm thinking cosine, because cosine has 2n factorial. Which you should all know. Yes, you need to have it memorized. Would be this. Hi. I'm recording, so please keep it down for a little while. More people walked in. Christy, Crystal's sister, and Christina, but not Christina who's in my class, just Christy's groupie. So now they're in the video too. Yay. So that's cosine of x. So what would x have been if there were no x in here, right? If you said or thought, oh, I bet it's cosine of 1, because then that would be replacing the x with 1, and replacing the x with 1 would do that. And 1 to the 2n is nothing, is 1. Look how fast I'm writing. See? And that matches that. Matchy matchy. Now, because again, I think this was confusing, I'll give you one more example. The example I gave at lunch today. So if someone walked up to you and said, oh, here's a brain teaser. What's this guy? You might rightly panic until you think about elementary series. Which elementary series has n factorial on the bottom? There's only one of them. If you said or thought e, you're right. Because e to the x looks like this. That's how it would look, the number and sign. So I think, oh, what would replace x in this formula? Natural log. So that's e to the natural log of 5. Or, alternatively, a very eccentric way to write the number 5. Okay? That series evaluates the 5. And you can know that in seconds flat. Or you can struggle on the test for a very long time trying to come up with how do I find it where it converges. Because it's not a geometric series, and that's the only other thing you know how to find the actual value of. Oh, for the record, cosine of 1 was 0.5430. Very accurate. Very accurate. This kind of ways, I think I talked about this in the Taylor lesson, although I haven't recorded this yet. That's why Taylor series are so widely used. Your calculator doesn't have to use that many terms to get that level of accuracy. It's pretty cool. So when they ask you to find an actual value, they're asking you to use an elementary series or to use the actual function. Okay? I'm going to even insert a page. So, actual value, because again, this will help the BC kids about to take this test. Would usually be f of x. Like the actual value when you plug it in. For Taylor series, we're talking about the approximate value being t of x, a Taylor polynomial, and the error being something else, right? The error is the absolute value of this. So they've asked you to find the error, the actual error, compared to your error bound, your approximate error, that's how you would do it. That'll help you on the homework more than you know. I'll try the pause feature again. Oh. Alright, so the light's flashing again. I can't wait to see if this worked. So nervous. Oh, I inserted before. Oops. Well, there's the error slides one more time. Okay. So, here's the error you would use for Taylor series. I want to say the remainder, or the error, is still the first unused term. It's still the first unused term. So I think this would have helped also in class, because here the approximation for our series, I'll color that with the error color. The approximation we're using is, here's the actual value. And remember, this guy is actually equal to, this is what the Taylor series formula is, in case you forgot. The nth derivative, that's what that notation means. And I'll even write it out one more term, which I don't usually do, just to emphasize what we're talking about. The n plus first derivative. Oh, shrinky. Not evaluated at x, evaluated at c. And this ... is really important because I said equal. So that's what f of x says. That's the actual value, remember, in red. That's my actual value. If I actually went through and added up all of this, which is not impossible, we just did it, cosine of 1 in the last example, that would be the actual value of everything. That would be the actual value. The idea here is if I'm approximating it, the approximate value we'll approximate the value is to just use the first n terms. So that this is my first unused term. I would have had f of c. I would have had f prime of c times x minus c. And always remember, it's the first four terms and the first the first four terms and the general terms. But I'm not actually going to write that out because I'm trying to save time. So my approximate value for the Taylor series, if I stopped at n, that would be the approximation. And what this formula is saying is that this becomes the error. This becomes the first unused term. That becomes the first unused term. There's many, many, many other unused terms, but that's the first one. So that's why that's the error. And that would be the approximation. So again, that's like the Taylor polynomial, like I was just saying in the last one. That's the Taylor polynomial with degree n. Sometimes you'll see this p sub n. Taylor polynomial with degree n. Okay. Now, for non-alternating series, we're going to copy this all over. It's very important that you understand all this. For non-alternating series, you can't just use the first unused term. You have to be more clever than that. For non-alternating series, you have to use this formula called the Lagrange error bound. The Lagrange remainder. Sorry, and again, this is what confused the BC kids. Remainder. Error. Bound. Okay? Those are the same thing. The Lagrange remainder, or the error bound. Is this formula, which is very, very close to this formula. It's still mostly based on the next unused term, right? If I was going to highlight stuff, we'd have that highlighted. I don't know if I can even write that small. But the key difference between the Lagrange remainder and the alternating series remainder, and this is the key to one of the questions on the homework, is that this is C and that is Z. So let's read about what Z is now that we finally finished discussing all around. Z is the X value between X and C, between the value itself and the center, right? That would make this a maximum, which makes the n plus first derivative at z a maximum. So this is a y value, right, of n plus first deriv, a maximum, which makes the absolute value a maximum. So we're going to use the biggest value that this can become. Sometimes authors just write this whole thing. They just replace this whole thing with m, just to help you think it's just one number. It's not that x value, it's the x value plugged in here. So the way these go, the way these problems will usually go, it will start out by a very simple process. Oh wait, let's finish talking about this, I'm sorry. So we're going to choose a value which will make this factor a maximum value. It could be the center. It could be the x value where we're going to evaluate. Or some other maximum value in advance. For instance, if I know the series is sine, or if I know the nth derivative is sine, or I know the nth derivative is cosine, I know the maximum value is 1. Because I know sine and cosine have maxes, really easy maxes that you need to know of 1. So to give you more help, I grabbed the title. I don't usually lock the title. It's a little known secret. So let's just hide it. This will have 3 steps. We're going to find out what n is. Yeah, step 1 again. Find x. Find x. Valued at. This is usually called degree. That's a keyword you're looking for. We're going to have to find the center, or centered at, right? And then you'll worry about well, not what, let's say, how big can the n plus first derivative get? How big can it get, really? 1 for sine and cosine. You usually have to have some other way of finding that out. They might tell you a function. They might do some other way, but usually you have to find that out. Okay, that's the hardest part. This is the hardest part. This is all procedural. What degree do they want me to use? What am I trying to approximate? What am I trying to approximate? And what's the center? Here we go. Estimate e squared using a Maclaurin polynomial of degree 10 for e to the x. So a Maclaurin polynomial, Taylor polynomial, centered at 0, right? C equals 0, okay? A degree 10. Guess what? The standard series you memorize for E is the Maclaurin polynomial. So I'm going to estimate. So e to the x is approximately 1 plus x. And you should be able to do this pretty quickly. X squared over 2 factorial. X cubed, 2 factorial is 2. It's okay if you wrote 2 there. X to the 4th over 4 factorial. X to the 5th over 5 factorial. X to the 6th over 6 factorial. X to the 7th over 7 factorial. Degree 10, I'm looking for an exponent of 10. I'm looking for the exponent of 10. Okay. So that's what e to the x is, approximately. Why approximately? There's no dot dot dot. So the idea then is that e squared, some students like to plug in e squared to all the x's. I think about x is in the exponent. What's in the exponent? 2. Approximate again, 1 plus 2. 2 squared over 2. 2 cubed over 3 factorial. 2 to the 4th over 4 factorial. 2 to the 5th. To the 7th, all the way up to 10. Now, I think in class at this point, I got a question like, do we really have to write that out? No. That's probably not necessary. But this is. What I'm writing now definitely is. Showing that you know how it goes. Showing that you know how we're approximating it. That's a 9 in the exponent. That's a 9 in the exponent. Use the Lagrange form of the remainder. Ever. See? I do use them together. To estimate the accuracy. So, degree 10. Again, n was 10. What was the first unused value of n? The first unused value was 11, which would be n plus 1. So n equals 10. C equals 0. C equals 0. What does it say? Evaluated at x equals 2. So x was equal to 2. I'll use blue, right? Because we are equal. So here I go. The Lagrange error bound formula. The absolute value. Sometimes you call it the Lagrange remainder. LR, Lagrange remainder, is less than or equal to, okay? n plus 1 everywhere. So it's the n plus 1 derivative evaluated at z, where this will be maximized, times 2, sorry, let's write it out like x minus c, the 11, 10 maybe, over 11 factorial. Alright, again, x was 2. Why? Because I was plugging in 2 for x up here. So, we're talking about and c was 0, so 2 minus 0. That's how I got 2 to the 11th. I do remember a lot of confusion about where that 2 came from. 2 minus 0, that's center. Okay, that's how I got that 2. Alright, now what's the 11th derivative of f? What is f up here? Right here. That's f of x. Now e to the x is one of the only functions, sine and cosine are the other ones, where you should be able to know the 11th derivative like that. What is the 11th derivative of e to the x? The 11th derivative of e to the x, I don't know if you can hear the people outside. I'm sorry. Always like this, 11's kind of hard because you might think that's a double prime, but it's not. Is e to the x. If you say without e to the x, that's great. So now it's the 11th derivative evaluated where? What kind of function is this? Is this an increasing function or a decreasing function? Do you know? It is increasing. So the maximum value here on the interval from, oh, that's not sigma. We're talking about maximum from 0 to 2. Right? So the question is, where is this maximum? Is this max on that interval? Where is it maximized? It's not here, because it's growing. So what we're talking about is z equals 2. The x location of max. So max value on is e squared. I plug that z into there, into the derivative. It's f of 2, sorry, the 11th derivative of f evaluated at 2, which is e squared. That's ugly. So what we're talking about is, again, that was the max value. That's what's going to go in there. So the Lagrange remainder, so it was over here. This whole value is at least as big as e squared times 2 to the 11th over 11 factorial. Which is something like .000379. If you punch it in your calculator. Now, I'm going to write it out one more time because, highlight in pink even, because max value of the 11th derivative on 0 to 2. Evaluated at centered. Centered at 0, evaluated at. It's always that interval. That's e squared. If you're thinking right now that this error is not really useful because I'm trying to approximate e squared and tell me how bad of an approximation it was, I'm using e squared, you're right. Don't worry about that too much. That's just a philosophical thing. The problems on the test are usually more understandable. It's not e squared, it's you'd be using 0. So you'll be getting 1 here. Okay, that makes more sense. So don't get back down in there. The process. What was the degree? N plus 1. X. C. To the n plus 1. N plus 1. Match, match, match. 2 minus 0. 2. Okay. The hardest part is why are we using the 11th derivative? Well, 11th derivative is easy to understand. But what do we want about it? We want the maximum value on the interval. So let's do another problem. Slightly more approachable. The 5th derivative of x evaluated at, is 700 sine x. If x equals 0.07 is in the convergence interval, or the power series, centered at x equals 0, so it's a Lagrange series, find an upper limit for the error in the 4th degree, Taylor polynomial is used to approximate f of 7, f of 0.7. So there's 0.7. And here's the key phrase that was throwing out for all my AB kids. All my BC kids. Upper limit for the error. Remainder. It doesn't say alternating, so Lagrange. These are the keywords you should be thinking about whenever you hear upper limit for the error. Okay, and they're talking about Taylor polynomials. There's only one game in town. So it's that same formula again, which I'll write down just so you don't have to flip around. The n plus first derivative, evaluated at z, the maximum value of this, times x minus c to the n plus 1 power, all over n plus 1 factorial. So, again, first let's settle what's n. Where do I see the word degree? I see it right here. It's 4th degree. Now that's really convenient, cough, 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 because they're giving me the 5th derivative, which would be 4 plus 1. So that had to match, okay? If you're getting weird stuff, if you think n is 5, so using 6, you're asking how would I get 6? Like, I don't know. 4th degree Taylor polynomial. So the first unused thing was the 5th. Okay. Centered at x equals 0. That's c equals 0 again. That's what's telling you right there. And we're plugging in 0.7. So you really should be able to get, without much hesitation, that the Lagrange remainder is less than or equal to the absolute value of f, in this case 5, because 4 plus 1 is 5, x is 0.7, c is 0, n plus 1 is still 5, all over 5 factorial. Again, matchy, matchy, matchy. So the question is, this buckaroo. How to maximize. Luckily, and again, I'm saying luckily sarcastically, it had to work out this way. The fifth derivative of z, of f at z, is right there. Right? I can't emphasize this enough. You need to understand that's right where it is. 700 sine z. Since sine of z is less than 1, or equal, always, the fifth derivative evaluated at z is less than or equal to 700 times 1. If I use the maximum value for sine, then the rest of everything has to get maximized, which is obviously equal to 700 x. Okay. So again, we're going to replace that with 700. Everything else is the same. 0.7 to the fifth over 5 factorial. As always, I'm going to put absolute value bars, not because I need to, this is definitely a positive number, but because I feel safe. Because it makes me feel nice and safe feelings. And if you calculate that decimal out, which you need to be able to do, you get 0.9804. That's all we need to do. That's it. That's how bad of an approximation this thing is. At this x value, when it's centered here, that's all you need to know. You don't need to know anything else about the series. You don't need to know what function this was. You don't even have to think about what function that was. I don't know if you can hear that. It's getting really annoying in here, though. Rakesh, could you shut the windows, please? I don't even know if it's picking up on the audio up here, but I can't. There are people just shouting 1, 2, 3 outside. I bet it's like tennis or some sport I hate. You can lock the window too, Rakesh. Thank you. Thank you very much, Michelle and Rakesh. Michelle's in the video now too. Okay. Alright, here we go. All I wanted to mention was that a slightly better answer we know we are trying to maximize, we're trying to maximize the fifth derivative on the interval from 0 to 0.7. So we can use so sine's increasing until about pi over 2, 0.7 is less than pi over 2. Pi over 2 is about 1.7-ish, right? So we can use e equals 0.7 for the fifth derivative at 0.7, which is 700 times sine of 0.7, which would be 450.952, which is much lower than that. If we use that value, the Lagrange remainder would be lower than 0.631596. You don't have to be that clever. One will always work for sine and cosine, okay? However, again, this is a much smarter way to do things. It just requires a calculator right here. It's a much smarter way to do things because that's a much lower error. This is off by almost one whole unit. One whole mile. This is only off by 0.6 miles, which still sounds like a lot. That's much better than 1 mile. It's 0.4 of a mile better. Okay? And I got that number by doing the same exact process. That would be the same. That would be the same. That's the number that's changing. Okay, last example. Okay, so here they tell you something interesting. Let's highlight it. That's a decreasing function. I bet that'll be important. Find the error-bound Lagrange remainder. Lagrange remainder. When a fifth degree, fifth degree, I'm holding on to the word degree. Taylor polynomial is centered at x equals 4, centered at, is used to approximate f of 4.1. Assume the series converges for x equals 4.1. That's just telling you that the series is working, that this whole thing works. Remember, the first thing we talked about was we needed it to converge. Alright, so if that's what we're trying to approximate, what is the x value? X equals 4.1. Now they kind of give it away right there. But that's what we're trying to approximate because that's what's inside f. If we didn't have this sentence, we'd still know x equals 4.1 because that's what's inside f. Centered at x equals 4. C equals 4. Fifth degree. N equals 5. So n plus 1 would be 6. Then checks out. You can always error check. I'm going to write it down one more time just so you can see how everything's working. I want the sixth derivative evaluated z. Sorry, I'm going to write it down more carefully. N plus 1. X minus c to the n plus 1 power. All over n plus 1 factorial. Okay, I found n. All it takes to be good at Lagrange remainder is just being able to work with the formula. Do what it's asking you to do. So the Lagrange remainder. N is 5, so n plus 1, everywhere I see n plus 1 is going to be 6. 6. That's really good because I know something about the sixth derivative. I don't know anything about any of the other derivatives. Everything is really cagey. 4.1 minus 4. That's convenient. XC. 6th power. 6 factorial. Now, again, I want to find max value. Now here they don't give us something like sine, so we have to, they don't give us a formula to find max value on the interval from between here and here, 4 to 4.1. So where will that be maximum? If it's decreasing, if this function is decreasing, its maximum value, since f to the 6 is decreasing, z equals 4. Right? We're talking about something that looks like this. Womp. That's going to be the maximum value. Yes? Yes. So, We'll rewrite this. Lagrange remainder less than or equal to absolute value. The sixth derivative at 4.1 to the 6 factorial. I can't find the value of that because I don't know. I don't know what this function is, but that's the formula for it. If some crazy person told you what this value was, you could punch this in a calculator and find it. So if my BC kids are any indication, you might want to watch this video again. You might want to watch this video while you're doing the homework. I don't know what you want to do. Replay the key parts. It's not that bad. It can be very confusing. Just pay attention, pay careful attention to all of the words. The problem will always tell you about error, remainder, actual value, approximate value. Okay, I hope I did a better job explaining this. BC kids watching, I don't know. Shout out to all of you. Leave a comment in the video telling me how much better I did now. Maybe. Maybe I did, maybe I didn't. Keep up the hard work. Make sure you do the assignment. This assignment is very important. There are problems on this assignment that are actually AP test style problems. So, do the assignment, 8-1. Keep up the hard work. I don't know. Have a nice night. Have a nice day. Talk to you later. Bye-bye.